Okay, so we're now ready to do likelihood models. Okay, so now we're not doing like the Heckman two-step where we do linear regression in one of the equations. We're going to work with maximizing likelihood functions or partial likelihood functions for both the structural equation of interest and the selection equation. So this means that we need to impose more structure. We have not assumed anything about the distribution of the error term in the equation of interest. We just assumed that was correlated with the variable in the selection equation, the V2, that was normally distributed. Okay, that doesn't mean that U1 needs to be normally distributed. Okay, so in order to make any progress with maximum likelihood, we need to specify the distribution of the unobservables. And so that's what we're going to do. And that means that we are imposing more structure. Okay, so the previous approach is in some sense more robust in the sense that we're not imposing as much structure. Okay, so just a little bit of review. If we, for regression models, we can ignore selection if the selection indicator is a deterministic function of the explanatory variables, or if the selection is independent of both the explanatory variables and the unobservables in the equation of interest, or y1 given x1, if you will. Okay, so for likelihood models, in the previous lecture on, for example, binary response, we worked with conditional densities, right? It's not enough to just work with the conditional mean or so that you get like a regression function. You need to work with the conditional density of the variable of interest and not just the conditional mean, okay? But we're going to use that what we worked on previously when we were studying binary response to derive this density, okay? Actually, in neither of these two cases mentioned above, if they are not met, well, then we need to explicitly take account for the selection in a joint estimation. And so it's not enough to just to do like the conditional distribution of y given x1. Well, we need to again condition on selection because that is the data that we have. We have data on the selection selected sample. Well, in order to do that, well, we need to actually specify the joint distribution of the outcome variable and the selection variable. And so now we need to impose more structure. Okay, but by the way, yeah, so here in the context of y1 being basically a linear, having a linear relationship between with x1 and some error term, then this would be this would be like the density from a linear regression model with, for example, normally distributed errors. Okay, otherwise it would be if y1 could be like a binary indicator, then and errors were normally distributed, then this would, for example, be like the probability of density of or the density from the probit model, right? But then again, we can't work with that, right? Because we have a selected sample. So if we have a selected sample, well, we need to derive that density conditional on selection, and in order to do that, we need to figure out or specify how these two variables are jointly determined. Okay, and that's what we're going to do. Okay, so just to write up some of the equations to get a little bit of a notation clear, the structural model without selection, that would be the conditional density for y1 given x1, just like we had previously, like in a binary probit model. That would be the density, or what would be looking like the likelihood contribution for the binary probit model. For example, again, we can't do a binary probit because we are worried about selection. So we have a selection model that describes how selection is occurring conditional on a set of explanatory variables. And again, we're going to use the same notation as before. So X may hold both variables that affects selection and the wage equation here, or the structural equation of interest. Okay, so it's both have X both have X1 and another variable X2. Okay, so selection is generally ignorable if the density where we condition on selection is equal to this original conditional density. Okay, in that case, you could just do if y was a binary variable, then you do it, your usual probit. Okay, if it's a if y is is equal to x beta plus u, and u is normally distributed, well, then you just do a linear regression, and you can do that with maximum likelihood too, and it's going to be equal to the OLS estimator. And so this relationship, well, that's kind of the trivial relationship. That's not where we are, why we're here. This happens when S is a deterministic function of X, and if S is independent of Y1 and X1. So basically, the first two cases we covered, that's kind of, reminiscent of these two cases, case one and case two, where you just take like the conditional on a regressor, or you take a random sample, as saying the result from there, the insights there, it applies here. It's just now that independence have not just to be mean independent, but entirely conditional independent. So that's very, very similar to what we found in the beginning. Now, in order to move forward, well, we need to specify the joint distribution of selection and the outcome variable y1, okay, conditional on x1, not on selection. How can you write that? Well, you can write it as a product of two conditional distributions. So you have the conditional distribution of y1 given x1 and selection, and then you have the marginal for selection given x1. Okay. Now, actually, this last one here, that would be easier to estimate. It's just the density, the conditional density that enters into the likelihood for the selection equation. So if you have like a probit selection equation, that will be the conditional density for the probit model. Okay. Now there's going to be separate sets of parameters here. There's going to be parameters that determine this conditional density. That includes both that includes, once we condition on selection, that includes both the parameters that enter into the equation of interest. We'll call those theta m, and then the parameters that determine selection, that's called theta s. Okay, and that they're only entering in that equation here. Okay, so whereas theta m would not. Okay. So, an immediate thing to realize here is that we cannot use full maximum likelihood, okay? Because really we don't observe the entire distribution of y1 conditional on selection, or the joint distribution. We don't observe that, okay? So we can't. The problem is we only observe y1 when s is equal to 1. So this means that we cannot identify this joint distribution. We're kind of missing a part of it. That is the case where s is equal to 0. Okay, and so essentially, you can say, or formally, you can say that the density for y1 conditional on x, when you condition on not being selected, well, that's not identified, right? Because we don't observe what y1 is when we are not selecting the samples. Essentially, y1 is unobserved when the selection indicator is equal to 0. So we can never hope to really identify this conditional density, and so that means we need to continue with partial maximum likelihood instead of doing a full-blown conditional maximum likelihood using this entire expression. Okay, but fortunately, we can still move on, and it turns out that you can still identify the entire vector of structural parameters. This could be shown with partial maximum likelihood by ignoring that part of the density that we simply cannot observe. And you might ask, okay, well, you're ignoring that part of the density. That's saying we're not trying to fit that density with the structural parameters, so we don't have the restrictions from that density to pin down what the structural parameters might be. But since basically the model parameters here in the selection parameters, they are also contributed to explaining the density conditional on selection. Well, you move those parameters around, that's gonna change that density, and that gives us identification. So it can be shown that you can identify the entire parameter vector and find it as an argument that maximizes the expected value of this partial likelihood. Okay, so what is the difference? Well, the problem, the issue is that we really do not have this density for s equal to 0, right? We only have it when s is equal to 1, and so that's essentially sufficient. So we can work with this partial likelihood instead. So we can completely disregard the unidentified part of the likelihood. And so we can also show that basically either these two sets of parameters, well, they can be identified by estimating these two equations separately. So in other words, the parameters that it's entering into the selection equations are not restricted to depend on parameters in the structural equation. And in order to obtain, we don't need to impose that in order to obtain identification. So that's kind of the formal motivation for this two-step procedure that we just covered with the Hackett procedure. Okay, and this means that we can divide it into the two-step procedure and still obtain identification. So you get your selection equation parameters. You can identify those by essentially maximizing the expected log likelihood from the selection equation. And intuitively, it makes sense, right? You're looking at the coefficient in that selection equation. You can easily estimate that, right? And so the parameters from that equation does not enter from the model equation, does not enter there, so you don't need to know those. Okay. And then you can afterwards essentially, given that you have identified those parameters from the selection equation, then holding fixed those parameters, you can in a second step estimate the model parameters from the structural equation of interest, holding fixed what we've just identified as the true parameters, and then only varying this guy here. Okay, so that's kind of the argument for being able to do this this two-step procedure. Anyway, so if that was rather hairy, let's just take an example. So here's the example that we have already actually looked at. A linear regression model here, where y1 is like a continuous variable that is observed, and x1 is observed, but with a proper selection equation, so that actually x1 and y1 are only observed whenever the selection indicator is positive. So these two equations are completely identical to what we had before for the Hackett procedure. So now here they have Heckman sample selection equation model. And so what we would assume there would be that the conditional mean of u given x was equal to 0, so that it was we would make it like a conditional mean assumption about this. We would assume that this was normally distributed, conditional on x, with 0 mean and a variance of 1. And so now we can replace those latter assumptions by assuming that U1 and V2, they are jointly normally distributed or multivariate normally distributed with 0 means each of them and this variance covariance matrix. Okay, let's just take these parts one by one. Why is the variance 1 of V2? Well, we need to make the scale normalization because this is a binary outcome. So we need to use the usual scale normalization to have the variance of this guy equal to 1. That's again without loss of generality, because if you try to put in like a variance parameter here, you can essentially just scale up and down this parameter delta, and you would not be able to identify the parameters of interest here. And it's without loss of generality because you really capture the probability for selection completely just by after this normalization. Okay, now let's talk about this guy here. Well, that's a variance of U1. So now we're giving it, we're specifying what the variance is. It's a parameter to estimate. Okay. So and then these two here, well, what is that? That is the correlation between, or the covariances between U1 and V2. Well, if these covariances are zero, it means that these two variables are mutually independent, and then you would not have a selection problem, and you would, you could need to move on. So really, we need to figure out if this parameter here is potentially non-zero. Okay, so what the additional level of assumption that we're making here is that this is normally distributed. We already assume this is normally distributed. We haven't assumed this is normally distributed. And then with the assumption that they were jointly correlated like we had before in the specified way, where you had, the conditional mean of u given v2 was equal to gamma 1 v2, you together with the normal assumption about this about u2, you're going to actually arrive at this specification. So that's the additional assumption we're making. We're assuming that u1 is normally distributed. Okay, so now we need to derive the density of y conditional on selection, and of course the explanatory variables. Okay, like we'll always do. Okay, so this is what we need to use. Again, we can use like Bayes' rule to decompose this conditional density into a simultaneous density divided by the marginal density for selection. Okay, so this is going to be essentially giving the conditional density here. This is just like standard statistics. And then this joint density here can be decomposed into these two parts. Actually, we already talked about that previously. But this joint density can be decomposed into these two conditional densities. That's also like standard rules in working manipulating distributions. You can get like a joint distribution by taking a conditional distribution times its marginal. Okay, so or the marginal for what you condition on. So everything here is right. And then the question is, what are all these different objects? Okay, now the first one, or actually the last one, this guy here. Well, that's the density for the selection indicator. Well, we know what that is, right? That is just the density from the ProPIP model, right? Because we know there's a selection indicator here. Well, that is coming from this ProPIP model, where you have this being a normally distributed variable. You end up with a ProPIP model, and these two outcomes, either s can be equal to 0 or it can be equal to 1. Okay, and then you get this expression here, just like we've seen in binary response models before. It's just now a binary outcome is a selection indicator. And then this guy here, well, this guy here, well, what is that? Well, that's a density of y conditional on x, but y is a linear equation with a normally distributed variable. So we know how to derive that conditional density. That's the one the same as you would have on a linear regression. So you would have like the residual normalized by the variance or the standard deviations put into the standard normal distribution. Then because you make this this is really just the density for a normal distribution with a variance of sigma 1 squared. Okay, so again, that's pretty standard. But there's still one part missing, and this is essentially the probability of selection conditional of y1 and x1. Okay, so what is that guy? Okay, we need to derive that. So that's what we're going to do now. Okay, so we can write so just to remind ourselves what the selection equation looks like. So we can rewrite this a little bit. So first, notice that since v1 and u2 v2 and u1, they're jointly normally distributed. Well, you can always write two normal distributed variables in this particular linear combination, where as a sum of two normal distributed variables. Okay, so here, if you write it in this way, well, then this is going to be normally distributed. This is normally distributed. So the sum of two normally distributed variables, well, that's normally distributed. So that clearly holds if E1 is normally distributed. And then it's just about figuring out what are the coefficients here. Okay, and they all have, both of these has mean 0, so you don't have to worry about the mean. Okay, now the coefficient here, theta, that's the ratio between the covariance between the two random variables u1 and v2, that is this guy here, divided by the standard deviation of u1. Okay, so that's essentially like the correlation coefficient, and so then we can write this just substituting in what u1 is from this from the structural equation. So that's the equation. Where do we have it? Right here, right? So it just subtract x1 beta to the other side, and then you got u. So that's what we have here in the bracket, and then plus our epsilon or our e1, that normally distributed variable. So then it's just left to consider what is really the variance and mean of this normally distributed variable. Well, it's going to be 0, right? Because this guy is 0, mean 0, and this is mean 0. So this is also going to have mean 0. And then it's all about computing that variance. Well, we know this guy here has a variance of 1, right? So you can use your standard formulas for calculating variances of sums of normally distributed variables. This something like the variance of one plus the variance of the other times the covariance between them, and then move that a little bit around, and then you figure out that the variance of this guy here must be 1 minus the covariance squared divided by the variance. Okay, so that is just an implication of the way we've written it here, and then the assumptions about the joint normality assumption, where the variance of this guy here is equal to 1. Okay, so now we actually have something we can work with here. Well, what do we have? We have the v2 v2 here, that expression. We have now an expression that depends on y1 and x1, so we can substitute that right back into this equation, and then what you have is essentially x delta plus delta x delta 2 plus this coefficient times y1 minus x beta. That's what you have here, right? But then and then we know that is normally distributive with this particular variance. So in order to calculate what the probability is for y equal to 1, well, then you just divide with the variance and become standard normally distributed. And then you got your probability. It looks very much like a appropriate probability, and it is. It's just with a different variance of 1 and with a mean that is equal to what we just derived. Okay, so now we're pretty much just done and need to put all these things together. We got all the bits and pieces. We got this, probability for selection equal to 1. We got the conditional density for y1 given x and conditional density of selection given x. So we got that. That's all we need to have in this expression here. Okay, so now let's put all this stuff together and put it into our likelihood function. Remember, this guy here, that's our partial likelihood. So that had only these two parts here, right? Remember, there was parts of the likelihood that we could not observe, so we're going to exclude that. Okay, this is coming from a previous slide. Yeah, where do we have that? Right here. This is what we have just derived, right? And so that was slide 39, and then we're using that on slide 43. And you're still puzzled, parse it and look at the workbook and see you can add these things together. And then essentially this first part here, well, that's what you just derived. This is the joint density for selection, the probability of selection conditional on y1. That's what we have here. Then we have the density for y1 right here. And then that's inside the logs, and that is that has to be multiplied with a selection indicator. So here we're essentially just summing over the sample where we have the selected sample and say that is the first n0 observations. Okay, so this is we could also just have multiplied with s the whole way through, and then summed over the entire sample, but then we will have like a bunch of zeros. Okay, and then we have the last part here, that is where we need to we sum over the entire sample, and then we get this stuff here. Yeah, so that's really what the partial likelihood function is. Now, things start to get a little bit hairy, but we can do it. So here's another example. That's an example with a propet with propet selection. Okay, so now the outcome variable y1 is no longer described by a linear regression model. It's described by a binary outcome model. Okay, so for example, if u1 here was normally distributed this week, we could estimate this by a propet if we had a random sample of y1 and x1. Yeah, again, we have the same issue that we only observe y1 and x1 whenever the selection indicator is equal to 1. Okay, so in order to estimate this model, well, we need to impose some structure that implies what the correlation is between these two variables. Okay, and that's what we're going to do here. We're going to assume u1 and v2 are jointly normally distributed with variances equal to 1, and then this correlation parameter gamma 1. And now the difference to what we had before in terms of the distributional assumption is now we're assuming that the variance of u1 is equal to 1, and that's does not have a separate parameter. Again, that's an artifact of the fact that we need to normalize the scale in the binary regression models or binary outcome models, because otherwise you don't fix that scale, you can't identify the parameter beta 1. So that's the usual deal when you have binary outcome models. You need to assume those disturbances in the linear indexes, they have variances equal to 1. But we still have this correlation, and again, not a surprise if these two things are correlated. You're gonna get zeros on the off diagonal, and then in that case you would not have selection problems. So here, in order to derive that density and to move on and do maximum likelihood, well, we need to derive the joint density again for the outcome variable y, and then the conditional or the selection indicator s. Okay, for propet with propet selection, that means we need to derive the conditional density of y1 conditional on selection and x, and then the probabilities of selection. The last one is easy, right? We've seen that before. That's just the density for the propet selection model. In fact, we can estimate this in the first step, and do full maximum likelihood on this part. We want to do these things jointly, so we still need to derive the conditional density of the variable of interest in the structural equation conditional on selection. That's a little bit more involved. So let's take a look at some equations. Here we're going to do actually the same similar trick as we did before with the use of the law of iterated expectations, where you first derive a density conditional on a variable, and then you take expectation with respect to that variable afterwards. So that's what we're going to do here. We're going to derive the density conditional on v2. Okay, now notice that this density that enters in here, that is conditional on v2. And then we're going to take the expectation with respect to v2 afterwards to kind of integrate it out, so that we get a density that is expressed in terms of observables. You observe the indicator for selection, and we observe x and we observe y when we have selection. Okay, now I'm not going to actually spend a lot of time deriving this, but the principles are very similar to what we had before. And notice, just in the case where we derived, where is it here? Where we derived this density, or the density for selection conditional on y. It's a way to derive a density for a binary variable. You're kind of following a lot of the same steps. It's all about finding out what is that variance of that residual term. That is what we have here, and so on and so forth. Write up the equations, and and then you should be able to actually verify, using the same logic, with manipulating around with your variance formula, exploiting that the variance of both of these error terms are equal to 1, and then you get this expression here. So anyway, just if you didn't really get it, just accept that it's looking like this. It's enough to illustrate the point I want to make. So here we've also recalled that this inverse Mills ratio, or well, this expression here, well, that is the density for a truncated normal distribution of V2 conditional selection, or equivalently the density for this particular normal distribution. So we kind of talked about this many times. So that is that conditional density. Okay. So what do you need to do in order to calculate that expectation? Well, what do you do when you calculate expectations? Well, of some nonlinear function of a random variable. Well, you take that nonlinear function with respect to the variable, and then you in this case this expression here, and then you integrate it over the support over the support of that random variable. And then weighted with its density. Okay, that's just what do we have here? It's really just a mean of a function of a stochastic variable V2 integrated with its density. And V2 is following its truncated normal distribution, so it has this density. And then what is the support? Well, that is the full support for this truncated density is from from minus from the truncation point to infinity. Okay, so that's where this distribution lives, because V2 is always greater than minus x delta 2. Okay, so that's the logic. So yeah, I know there's a lot of stuff going on here, but it's and maybe you don't want to end up estimating this model, but at least now you see an illustration of how you can calculate how you can calculate expectations of functions of random variables with respect to its density, and calculate also conditional densities by integrating over the density with respect to its with respect to the random variable over the entire support. Okay, so now, okay, that was kind of a little bit hairy. We're still left with this expression here. So what is that we just calculated? Well, that's the probability that y is equal to 1 given that the selection is equal to 1. Okay, well, that's what we needed, right? Together with the probability of selection, with these two terms, we have the entire likelihood. So, and this guy we already derived, so we kind of almost ready to rock. And then we can write can derive the conditional density for y given selection, and given it's a binary outcome. Well, then we know that the probability for y equal to 1 is just y equal to 0 is just the probability. 1 minus the probability is equal to 1, and this expression here, we got it up here. Now it's getting more involved, right? We need to calculate integrals and so on to express these probabilities. But in principle, you can do it with what you've learned in numerical methods in the last year. Do a little bit of Gaussian quadrature, and you'll be able to evaluate this integral. Then let's just put all the things together to derive the partial likelihood. Again, you got the expression for the partial likelihood here, and then it's just putting in the bits and pieces that we have over here, that we have here. So that's pretty much it. And again, pause the video if you want to look at these expressions, and take a minute to dwell. Maybe try to write it down on pencil and paper yourself, and see if you can work it out. And if you can't, at least you got the formulas right now, and then you can implement that in your Python code. Something that I'm not going to do, because otherwise it's going to take too long to go through everything. Anyway, so let's just end with a discussion of some of the pros and cons of using the full structure and do these likelihood models. Well, basically, the one advantage is that you don't have to calculate take account for the generated regressor problem as we had in the Heckman sample selection model, where you estimated with a two-step procedure. You have this inverse Mills ratio that was based on the delta 2 that was estimated in the first step, that was subject to sampling error. Okay, and that sampling error, well, when you were estimating the equation of interest, where it was included as a generated regressor, you're not taking into account that sampling error when you calculate the variance covariance matrix for the parameters in the structural equation. So that meant that these standard errors were not valid. Well, now they are. Okay, so now you can use the standard variance covariance matrix for partial maximum likelihood. Since it's partial maximum likelihood, it's not maximum likelihood, so identity information identity is not holding. So you still use the robust variance covariance matrix, the ones with the structure A inverse B A inverse divided by n, and so that's really just coming out of the box once you've maximized the likelihood. Okay, so that's one of the advantages. Then one thing I'm not mentioning here on the slide, but need to say that's kind of the overall advantage. It says that partial maximum likelihood is the efficient thing to do. That's the best use of your data, given that the assumptions are holding, given that the model is well specified. It's the most efficient use of your data you can have. That's where you get the lowest standard errors. This is where you get the most precise estimates. Whereas the Heckman sample selection procedure, well, that is not imposing that structure that we have assumed is correct here. And so it's not efficiently using the data in the same way by imposing the normality assumption in the first step and that joint normality. Okay, but that's on the flip side. That's also a disadvantage. Suppose that the errors in the equation of interest are in fact not normally distributed. Well, then you violated that assumption. And so the Heckman procedure, the Heckman sample selection two-step procedure, that's valid even if the errors in the equation of interest, the U1s, are not normally distributed. Okay, so these are stronger assumptions, but given that you can estimate it under weaker assumptions, these assumptions are testable. So you can actually test whether these errors in the first step equations are in fact normally distributed. In fact, you can calculate. And so you can make a test whether that's true. Another disadvantage of this likelihood approach is that it's just numerically more challenging than Heckman. Well, if you take, for example, the procedure with the binary response in the equation of interest, with the one which is derived, there was an integral you need to calculate. Okay, that's numerically hairy to work with. But even in the case where you have this linear regression, well, you have more parameters that are estimated jointly, both those from the structural equation, the theta m's, and those from the selection equation, the theta s. So now it's a higher dimensional problem. It's a higher dimensional parameter space you need to search over. So your maximization routine is going to take more iterations and potentially also have some more difficulties in actually trying to actually find the maximum. Okay, so that's a potential issue. And yet again, then if you want to make this fast, well, then you want to calculate analytical derivatives, and then look at the equations which has been through. Maybe the analytical derivatives, they're also kind of it requires a little bit of work with the Greek letters. So that's kind of leading me to the last point here. There's just more Greek letters to juggle around, and things becomes a little bit more difficult. This is really the big selling point for the two-step estimators, is they're so easy to do. And if you have lots of data, maybe you should not worry so much about actually whether this is efficient. And even and oftentimes we're just interested in testing whether you have a selection problem. Then if you haven't got a selection problem, well, you can just do linear regression and not worry about it. If you have a selection problem, well, then maybe either you can bootstrap your standard errors to get valid inference, or you can essentially use whatever you found using your two-step approach as good starting values and put it into your likelihood model and estimate them, or in a more easy manner. Okay, so this was a little exercise in some more on these likelihood models, and next topic here is actually going in the exact opposite direction. Instead of imposing more structure, we impose less structure. Actually, we're not willing to make any distributional assumptions and try to see how far can we get, how much can we learn just from the information that is in the data, and to obtain identification without making these parametric assumptions. And that's what we're going to talk about in the last video from my end.